My talk will be about new tools for sustainable agriculture. I am Francisco Villalobos. I teach at the School of Agriculture at the University of Córdoba and do my research at the Institute for Sustainable Agriculture of the SIC in Spain. First of all, I would like to thank the organizers of this international scientific and practical conference, Priorities of the Agroindustrial Complex Scientific Discussion, which is dedicated to the 30th anniversary of the independence of the Republic of Kazakhstan. In principle, farmers and agronomists need specific tools for several reasons. First of all, to improve resource use and its efficiency for fertilizer, irrigation, seeds. We want also, in special for sustainable agriculture, to reduce the negative impacts of the agricultural activities. We want also to increase food security and the farmer's income. In some cases, it is important to improve the synergy with other sectors that are connected to agriculture, like seed companies or the food industry. And many times we have to analyze problems where experiments are too expensive or even impossible. And for that, we will talk about specifically about crop simulation models. There are many tools available today that might be used by agronomists or farmers to improve the efficiency of agriculture and the sustainability of the agricultural production. For instance, the use of sensors, which are becoming cheaper and cheaper, or satellite imagery, which is becoming more widespreadly used. But we will focus today on some decision support systems and also on crop simulation models. A decision support system is, in principle, a computer program that helps us making decisions in agriculture. As an example, here you see FertiliCalc, which is a very simple decision support system for fertilizer rate calculation. In this case, we developed this program at the University of Córdoba and CSIC to help farmers in calculating fertilizer rates, and it could be also be useful for teaching fertilizers. As of today, we have developed 88 versions for different languages, and we provide different tutorials and reading materials for anybody interested in the program. The program is freely available at the webpage of the University of Córdoba. This is the first form of FertiliCalc version 3, and this is specifically the Kazakh version that was developed with the help of some colleagues at the Kozyvayev Northern Kazakhstan State University, which I really appreciate for their help. In this program, the user first selects one or several crops and then adds for this crop the expected yield, the soil type here, also some soil data if some soil analysis is available, and also the user selects the strategy for phosphorus and potassium fertilizer. Once those selections have been made, the program shows the calculated requirements for nitrogen, phosphorus, and potassium in the upper part of the second form, and then the user can select different products, different fertilizer products. Like here, that we have selected, for instance, urea for nitrogen. Once we have selected products that meet the different requirements, we go to the third form where the results of the program are shown. And these results first include the fertilizer rates in the upper part, fertilizer amounts or the amounts of the different products to be applied, and the total cost per hectare. Then there is an indication, a calculation of the nitrogen losses by different processes. Third, we have an estimate of the potential acidification due to these fertilizer products. And finally, there is also a simple mass balance for calcium, magnesium, and sulfur. It also shows the balance for P and K, but if the calculations have been exact, the balance would be 0, which means that we are meeting the demand. A more sophisticated way of analyzing crop production is the use of crop simulation models, which are mathematical descriptions of the physiological, biological, physical performance of a crop. In fact, we try to include a mathematical description of all the relevant processes that result in crop yield, like the water balance, the photosynthesis of the crop, the growth of the different plant organs, etc. In principle, we will always require some inputs related to the soil characteristics and the weather data, but also about management and cultivar coefficients, etc. Today, many crop simulation models have been collected in a single package, which is in fact a decision support system for agro-technology transfer, DSSAT, that was first led this project by Professor Joe T. Ritchie at Michigan State University and Professor Jim Jones at the University of Florida. Today, Professor Garrett Hoogenboom at the University of Florida is the leader of this project. It includes many crop simulation models and other tools that may be used, and our contribution, the contribution of the University of Cordoba, was the development of a sunflower crop simulation model, which is called Oil Crop Sun. Here we see the interface of the DSSAT version 4.75. We expect the version 4.8 being released soon, and this includes many most important crop species globally, and also additional tools to manage weather data, soil data, to run simulations for crop rotations or do spatial simulations. The program is available for free at the webpage of the DSSAT project, dsat.net. Just an example of the use of DSSAT have been prepared to show what it does. In this case, I have been analyzing comparison of long rotations versus a short rotation of barley, and I have selected as location Petropavl at Kazakhstan. I have used the soil is a calcic Chernozem, a deep calcic Chernozem, and I have selected a crop sown on May the 15th, and I have done the simulations using generated weather data 25 years that were generated using Clima SD. We will talk about it later. And here we see the results of the simulation, combining this soil data, management data, and weather data, we have this result. You see that growing barley every year is at least equal or better than growing barley only one every other year. The average yield is improved with no fallow if we do continuous barley, which is 2 tons per hectare per year, as compared with a long fallow, which would give less than 1 ton per hectare per year. The variation among the different years is basically related to water availability. Here I have plotted the yields versus the seasonal transpiration, and you see that there is a close linear relationship between the yield and the transpiration for the different years. I have prepared another example, in this case analyzing nitrogen fertilization of barley at the same location in northern Kazakhstan, with also barley crop with the crop sown on 15th of May, and I have compared applying 0, 40, 80 or 120 kilograms of nitrogen per hectare, where the data were the same as used in the previous analysis. And here we see the results for 25 years of simulation, and we see that there is always a positive response to nitrogen, except in the 2 years that are shown by the arrows. There is little difference in yield when applying 80 or 120. If the price of fertilizer doubles the price of barley, then the optimum rate is 80 kilograms of nitrogen per hectare. I have mentioned that the weather data were generated using Clima SD, which is a weather generator that we developed at the University of Córdoba with the main purpose of feeding crop simulation models when we don't have daily weather data available. Here you see the web page where you can download it for free at the University of Córdoba. And this is the interface of the program that includes a large database which allows the direct use of the program, the direct calculation of generated weather data in many locations around the world. It also allows to change the mean temperature, or we can change the rainfall as a fixed percentage to generate data that would correspond to different scenarios of climate change. Once the weather data have been generated, we have the possibility of plotting the data. For instance, this is a location in Brazil, and this is the reference evapotranspiration throughout the year, or this would be the rainfall in millimeters per week in this Brazilian location. You see there is a distinctly dry period. Apart from the locations included in the large database, we can add other locations of our choice, defining the latitude, the longitude, etc. And we would require for that the average values of solar radiation, maximum and minimum temperature, rainfall, number of rainy days per month, wind, and vapor pressure. Thank you very much for your attention. Both Clima SD and FertiliCalc are available for free at the webpage of the University of Córdoba that is shown in here.